IFR training video, by
Toga thrust.
VOR theory. Introduction. System description. Using AVOR. Radial inbound. Radial. Failures and contingencies.
Introduction.
We are facing major changes in aviation, mainly in instrument flying. With the growing importance of satellite positioning, old-fashioned navigation and approach techniques will soon become obsolete. What about pilot core competencies? Are we bound to follow the line and nothing more, or should we keep training those procedures and techniques to keep what makes a pilot, mastering? You think right if you are watching this video. Let's train as a pilot. Satellite navigation and approach techniques will be a part of your training.
Theory.
System description. Very High Frequency Omnidirectional Range Station, VOR,
is a type of short-range radio navigation system for aircraft, enabling aircraft with a receiving unit to determine its position and stay on course by receiving radio signals transmitted by a network of fixed ground radio beacons. It uses frequencies in the very high frequency, VHF, band from 108.00 MHz to 117.95 MHz. A VOR ground station uses a specialized antenna system to transmit both an amplitude-modulated and a frequency-modulated signal. Both modulations are done with a 30 Hz signal, but the phase is different. The phase of one of the modulation signals is dependent on the direction of transmission, while the phase of the other modulation signal is not, in order to serve as a reference. The receiver will demodulate both signals, and measure the phase difference. The phase difference is indicative of the bearing from the VOR station to the receiver relative to magnetic north. This line of position is called the VOR radial. A position line or line of position, LOP, is a line, or, on the surface of the Earth, a curve, that can be both identified on a chart, nautical chart or aeronautical chart, and translated to the surface of the Earth. The intersection of a minimum in position fixing to identify a navigator's location. The intersection of radials from two different VOR stations can be used to fix the position of the aircraft, as in earlier radio direction finding, RDF, systems. VOR stations are fairly short range. The signals are line of sight between transmitter and receiver and are useful for up to 200 nautical miles, 370 kilometers. The line of sight, also known as visual axis or sight line, also sight line, is an imaginary line between a viewer, spectator's eyes and a subject of interest, or their relative direction. Each station broadcasts a VHF radio composite signal, including the mentioned navigation and reference signal, station's identifier, and voice, if so equipped. The station's identifier is typically a 3-letter string in Morse code. The voice signal, if used, station name, in-flight recorded advisories, or live flight service broadcasts. Pictograms. AVOR.
VORDIC is a radio-based navigational aid for aircraft pilots, consisting of a co-located VHF omnidirectional range, and a tactical air navigation system, TACAN, beacon, where AVOR is TACAN. Civil aircraft can receive VOR, DME readings.
A tactical air navigation system, commonly referred to by the acronym TACAN, is a navigation system used by military aircraft. It provides the user with bearing and distance, slant range or hypotenuse, to a ground or shipborne station.
It is, a more accurate version of the VOR, DME system, that provides bearing and range information for civil aviation.
The DME portion of the TACAN system is available for civil use. Aircraft equipped with TACAN avionics can use this system for en route navigation, as well as non-precision approaches to landing fields. In aviation, distance measuring equipment, DME, is a radio navigation technology that measures the slant range, distance, between an aircraft and a ground station, by timing the propagation delay of radio signals, in the frequency band between 960 and 1215 MHz. And of visibility between the aircraft and ground station is required. An interrogator, airborne, initiates an exchange by transmitting a pulse pair, on an assigned channel, to the transponder ground station. The channel assignment specifies the carrier frequency, and the spacing between the pulses. On delay, the transponder replies by transmitting a pulse pair on a frequency that is offset from the interrogation frequency by 63 MHz, and having specified separation. Both types of beacons provide pilots azimuth information, but the VOR system is generally used by civil aircraft, and the TACAN system by military aircraft. However, the TACAN distance measuring equipment is also used for civil purposes, because civil DME equipment is built to match the military DME specifications. An aircraft can follow a specific path from station to station, by tuning into the successive stations on the VOR receiver, and then either following the desired course on a radiomagnetic indicator, RMI, or setting it on a course deviation indicator, CDI,
or a horizontal situation indicator, HSI, a more sophisticated version of the VOR indicator, and keeping a course pointer centered on the display. VOR signals provide considerably greater accuracy and reliability than NDB, due to a combination of factors. Most significant is that VOR provides a bearing from the station to the aircraft, which does not vary with wind or orientation of the aircraft. VHF radio diffraction, course bending, around terrain features and coastlines. Phase encoding suffers less interference from thunderstorms. VOR signals offer a predictable accuracy of 90 meters, 300 feet, as compared to the accuracy of unaugmented global positioning system, GPS, which is less than 13 meters. VOR stations, being VHF, operate on line of sight. This means that if, on a perfectly clear day, you cannot see the transmitter from the receiver antenna, or vice versa, the signal will be either imperceptible or unusable. This limits to the horizon, or closer if mountains intervene. Although the modern solid-state transmitting equipment requires much less maintenance than the older units, and an extensive network of stations, needed to provide reasonable coverage along main air routes, is a significant cost in operating current airway systems. Operations. VOR are assigned radio channels between 108.0 MHz and 117.95 MHz, with 50 kHz spacing. This is in the very high frequency, VHF, range. The first 4 MHz is shared system, ILS, band. The Instrument Landing System, ILS, is a precision radio navigation system that provides short-range guidance to aircraft, to allow them to approach a runway at night or in bad weather. In its original form, it allows an aircraft to approach until it is 200 feet, 61 meters, over the ground. Frequencies within the passband of 108.0 to 111.95 MHz, which have an even 100 kHz first digit after the decimal point, 108.0, 108.05, 108.20, 108.25, and so on, are RADIAL frequencies. While frequencies within the 108.0 to 111.95 MHz passband, with an odd 100 kHz first digit after the decimal point, 108.10, 108.15, 108.30, 108.35, and so on,
are reserved for ILS. The VOR encodes azimuth, direction from the station, as the phase relationship between a reference signal and a variable signal. One of them is amplitude modulated, and one is frequency modulated.
On conventional VOR, CVOR, the 30 Hz reference signal is FM on a 9960 Hz subcarrier.
On these VOR, the amplitude modulation is achieved by rotating a slightly directional antenna, exactly in phase with the reference signal at 30 revolutions per second.
Modern installations are Doppler VOR, DVOR, which is a circular array of typically 48 omnidirectional antennas and no moving parts.
The active antenna is moved around the circular array electronically, to create a Doppler effect, resulting in frequency modulation. Modulation is created by making the transmission power of antennas at the north position lower than at the south position. The role of amplitude and frequency modulation is thus swapped in this type of VOR. Decoding in the receiving aircraft happens in the same way for both types of VORs. The AM and FM 30 Hz components are detected, and then compared to determine the phase angle between them. The VOR signal also contains a modulated continuous wave, MCW, 7 words per minute, Morse code station identifier, and usually contains an amplitude modulated, AM, voice channel. This information is then fed over an analog or digital interface to one of four common types of indicators. A typical light airplane VOR indicator. A radiomagnetic indicator, RMI. A horizontal situation indicator, HSI. An area navigation, R. 1. A typical light airplane VOR indicator, sometimes called an omni-bearing indicator or OBI. It consists of a knob to rotate an omni-bearing selector, OBS, the OBS scale around the outside of the instrument, and a vertical course deviation indicator or CDI. The OBS is used to set the desired course, and the CDI is centered when the aircraft is on the selected course, or gives left, right steering commands to return to the course. An ambiguity, to, from, indicator, shows whether following the selected course would take the aircraft to, or away from the station. The indicator may also include a glide slope pointer for use when receiving full ILS signal. 2. A radiomagnetic indicator, RMI, features a course arrow superimposed on a rotating card, that shows the aircraft's current heading at the top of the dial. The tail of the course arrow points at the current radial from the station, and the head of the arrow points at the reciprocal, 180 degrees different, course to the station. An RMI may present information from more than one VOR or ADF receiver simultaneously. 3. A horizontal situation indicator, HSI, developed subsequently to the RMI, is considerably more expensive and complex than a standard VOR indicator, but combines heading information with the navigation display, in a much more user-friendly format, approximating a simplified moving map. Four, an area navigation, RNAV, system, is an onboard computer with display, and may include an up-to-date navigation database.
At least one VOR, DME station is required for the computer to plot aircraft position on a moving map, or to display course deviation waypoint, virtual VOR station. RNAV type systems have also been made to use two VORs or two DME to define a waypoint. These are typically referred to by other names, such as distance computing equipment for the dual VOR type, or DME for the type using more than one DME signal. In many cases, VOR stations have co-located distance measuring equipment, DME, or military tactical air navigation, TACAN. The latter includes both the DME distance feature, and a separate TACAN azimuth feature, that provides military pilots data similar to the civilian VOR.
in VOR. A co-located VOR and TACAN beacon is called a VORTIC.
A VOR co-located only with DME is called a VOR, DME.
A VOR radial with a DME distance allows a one-station position fix. Both VOR DME and VORTICs and VOR DME use a standardized scheme of VOR frequency to TACAN DME channel pairing, so that a specific VOR frequency is always paired with a specific co-located TACAN or DME channel. On civilian equipment, the VHF frequency is tuned, and the appropriate DME channel is automatically selected. While the operating principles are different, VORs share some characteristics with the localizer portion of ILS and the same antenna. Receiving equipment and indicator is used in the cockpit for both. When a VOR station is selected, the OBS is functional, and allows the pilot to select the desired radial to use for navigation. When a localizer frequency is selected, the OBS is not functional and the indicator is driven by a localizer converter, typically built into the receiver or indicator. VORs, airways, and the en route structure. VOR and the older NDB stations were traditionally used as intersections along airways. A typical airway will hop from station to station in straight lines. When flying in a commercial airliner, an observer will notice that the aircraft flies in straight lines, occasionally broken by a turn to a new course. These turns are often made as the aircraft passes over a VOR station, or at an intersection in the air defined by one or more VORs. Navigational reference points can also be defined by the point at which two radials from different VOR stations intersect, or by a VOR radial and a DME distance. This is the basic form of RNAV and allows navigation to points located away from VOR stations. As RNAV systems have become more common, in particular those based on GPS, more and more airways have been defined by such points, removing the need for some of the expensive ground-based VORs. RNAV can be defined as a method of navigation that permits aircraft operation on any within the coverage of station reference navigation signals, or within the limits of a self-contained system capability, or a combination of these. In many countries there are two separate systems of airway at lower and higher levels, the lower airways and upper air routes. Most aircraft equipped for instrument flight, IFR, have at least two VOR receivers. As well as providing a backup to the primary receiver, the second receiver radial to or from one VOR station, while watching the second receiver to see when a certain radial from another VOR station is crossed, allowing the aircraft's exact position at that moment to be determined, and giving the pilot the option of changing to the new radial if they wish. Using a VOR.
The way to get started is to quit talking and begin doing. Walt Disney.
If a pilot wants to approach the VOR station from due east, then the aircraft will have to fly due west to reach the station. The pilot will use the OBS to rotate the compass dial until the number 270 degrees aligns with the pointer, called the primary index, at the top of the dial. When the aircraft intercepts the 90 degrees radial, due east of the VOR station, the needle will be centered and the to, from, indicator will show to. Notice that the pilot sets the VOR to indicate the reciprocal. The aircraft will follow the 90 degrees radial while the VOR indicates that the course to the VOR station is 270 degrees. This is called proceeding inbound on the 090 radial. The pilot needs only to keep the needle centered to follow the course to the VOR station. If the needle drifts off center, the aircraft would be turned towards the needle until it is centered again. After the aircraft passes over the VOR station, the to, from, indicator will indicate from, and the aircraft is then proceeding outbound on the 270 degrees radial. Or go to full scale, in the cone of confusion directly over the station, but will recenter once the aircraft has flown a short distance beyond the station. In the illustration on the right, notice that the heading ring is set with 360 degrees north at the primary index, the needle is centered and the to, from, indicator is showing 2. The VOR is indicating that the aircraft is on the 360 degrees course, north, to the VOR station, i.e. the aircraft is south of the VOR station. If the to, from, indicator were showing from, it would mean the aircraft was on the 360 degrees radial from the VOR station, i.e. the aircraft is north of the VOR. Note that there is absolutely no indication of what direction the aircraft is flying. The aircraft could be flying due west and the snapshot of the VOR could be the moment when it crossed the 360 degrees radial. Radial inbound, radial. The blue aircraft is on the radial 150 degrees. It is heading 330 degrees, so is inbound to the station with a heading of 330 degrees, no wind, and so is on the radial 150 degrees inbound. The yellow aircraft is on the same radial 150 degrees, with a heading 150 degrees, no wind. It is outbound from the station on the radial 150 degrees with a heading 150 degrees. So it is on the radial 150 degrees outbound, or simply on the radial 150 degrees. Here, the aircraft is on radial 070 degrees, outbound.
Failures, irregularities and contingencies.
As a good pilot, you know that things are not always working as expected. So you are ready for as much as unexpected events as possible. Among those, what can you foresee? No talking about airport closure or aircraft technical defects such as engine failure or hydraulic failure, but only considering weather and/or navigation instruments.
Weather conditions.
In this case, VOR, there is no fallback available. If the weather falls below minimum values, your only option is to discontinue the approach and either proceed to enter a holding if you have fuel enough to wait for better weather conditions, or to go to an alternate with more friendly weather forecasts. Of course, as a good pilot, you already plan that, if you were to decide to divert, you would go to such airport that has such conditions according the destination alternate rules.
Instruments.
What can go wrong with my indications? On ground. Failure of the VOR station. Aircraft side.
Failure of the OBS, RMI, HSI. Screen, IFIS.
Failure of the instrument.
You have no more indications on your PFD about your VOR positioning. Above 1000 feet AGL, you can reconfigure to another type of approach, reset your minimas, brief the approach differences and the before 1000 feet AGL, then you can continue the new approach, if not, go around. Do not forget that, now, you need new RVR minimas and ceiling, for 2D, to be authorized to start the approach. Below 1000 feet AGL, go around and prepare for another type of approach. No real need to consider a diversion as the problem is coming from your equipment. Of course, if VOR is the only approach available, you have to change approach, or divert to another airport where you can use a different approach type.
Failures indications.
NAV flag. Loss of oral identification. Single needle system, needle parked at 90 degrees position, 3 o'clock. Dual needle system, with VOR set to the same frequency.
Failures procedure.
Check NAV control panel. Cycle frequency selector. Select another station. Coordinate with ATC. Request radar vectors.
Failure of the screen, AFIS.
On the G1000, you have an automatic changeover feature that switch your MFD to APFD, and you recover all your informations to be able to shoot your VOR. You will still have a GPS map through the inset feature.